unstable. It's not the greatest tripod in the whole world. It's kind of flimsy, the legs of it themselves. All right. I have done a couple of things here recently, as in today. I have gone back in and actually updated the course calendar for this class to make it actually accurate or to how things are happening. We are on May 25th, week 8, and the last lecture on the last assignment is today for assignment 10, and that'll be it. Assignment number 9, the cam displacement diagram, is due today. That is a printed out B-size drawing, and I have some to hand back from people that turned some in Tuesday. Next week, there is no class session and no open lab next Tuesday. I'm taking half a day personal leave because I have to use it up or I don't get it. So I'm going to take it. I've got some retirement paperwork I have to do, and that's just the way it is. So don't expect anybody to be here next Tuesday.
Is that for evening class too?
Evening class will still be in existence. No, it's just for the kinematics class. You don't get any time off for that. If I'm here, you're here. Assignment number 10 that I'm giving out today is the first submission will be due next Thursday, June the 1st. And then any and all first submission drawings need to be into me Tuesday, June the 6th. And all corrected drawings that have to be corrected need to be turned in Tuesday, June 13th, and that's it. There will be no drawings that will be accepted after that point. I have to get my grading done because I'm leaving. So I don't want to be here till Friday. We're working on it over the weekend or whatever. So that's it. Which means there will be open lab June 1st, June 6th, and June 8th that you can come in and work on assignments, anything that needs to be taken care of. All right, questions? Crystal clear. All right. Then the assignment. Let me go back up here to content. Assignment 8 is still in here. We did not do assignment number 8. There was just a bunch of drawing to be done, and I gave you a break on that. So assignment number 10. The actual assignment itself as a document is chapter 22 out of the textbook, section 22 about plate cams, pages 91 to 96. It would probably benefit you to go in and take a look at that. On page 109, assignment for unit 22-2 plate cam, assignment number 2. Complete the assignment to design a plate cam based on the information given. Make a drawing of the profile of the plate cam. In place of the chart on the drawing showing the angular displacements every 18 degrees or 12 degrees, dimension the drawing following the example shown on page 94. I'll go back and pull that page up and show you what I mean, as well as page 95 in the textbook. The drawing will include the cam displacement diagram as well as the cam profile and a side view. It will be best to do it on a C-size drawing. You should do it on a C-size drawing. Maybe I should say that. You did assignment number 9 to create a cam displacement diagram. In order for you to know the process, I have drawn the cam displacement diagram for you in this assignment to make it a little easier. You're welcome. And the following drawing is to be used as a starting point for assignment number 10. It's accessible on the M drive, student file share, M drive, CAD folder, CAD 255 kinematic drafting folder, AutoCAD drawing folder, and the drawing name will be CAD 255 assignment 10 drawing. It is also available in the D2L folder as CAD 255, or maybe it's just assignment drawing. I'll take a look at that. All right, title is going to be plate cam profile. That's height is 5/32 of an inch. The drawing number is KIN 255-10. The height of that is 1/8 of an inch. Yes. This is a 1-to-1 ratio drawing. It's just full size, 1-to-1. And then here it is, due at the end of class on Thursday, June the 1st. It's not a very difficult drawing. It's kind of tedious to put it together in a way, but it's not that hard. You just have to keep your mind about you. All right, any questions on that? All right. Then let's take a look at the textbook. Our wonderful little projector here that never seems to quite focus. Here's page 109. You know, as soon as I leave, they'll get a new video projector in here that'll be crystal clear. That's probably what will happen. They kind of threatened that they were going to replace it this year, but I never followed up on it. That's probably my fault. Hey, what about our new video camera? All right, a plate cam that will activate a diameter 0.50 inch roller follower. So that's the diameter of the roller follower, 1/2 inch. The design criteria is it's going to rise 1.5 inches in 180 degrees with harmonic motion. It'll dwell for 30 degrees. It'll drop 1.5 inches in 120 degrees with modified uniform motion and dwell for the remainder. There is something called the prime circle that is 3 inches in diameter. I'll explain that more fully when I pull up the AutoCAD drawing. The plate thickness of the cam is 1/2 inch. The shaft that's going to go through the plate is 1 inch in diameter. The hub that's attached to the plate that the shaft is going to go through is 1 3/4 inch in diameter by 1.5 inches long, and the key seat needs to be sized to suit that, although you'll probably find in the drawing that I gave you it's already been sized and it's correct, so you can go back and verify that. I know you will. You'll want to go back and check to make sure that I did the right numbers here. All right, in the example drawing in the textbook, and in this assignment, it says to add a chart to the drawing showing angular and radial displacements every 15 degrees, taking the radial measurements from the prime circle. We're going to do some of that. You're not going to do all of this in here. We're actually going to draw it up a little differently and not include a chart. So that's the actual assignment that you can go back and reference. And the drawing will end up looking like this. When I get done talking about this particular project, I'll pull the screen up and the sample drawing, full size, will be behind here on the C-size drawing that you can take a look at. Also in D2L, there is a PDF that you can access of the So the AutoCAD start drawing, which I'll get to, that's the cam displacement diagram, and the PDF sample drawing is available to you, as well as your cell phones and taking a picture of the drawing that you put away that you seem to like to do. All right, questions so far at all? You don't know enough to ask the questions. All right, then let's dive in here. This is already in the drawing, and just like assignment number 9, slightly over to the side. Just like in assignment number 9, you're going to use Arial font, bold font size style, 0.10 height for the indicators of where the rise starts and stops increments, where the dwell period stops, where the drop starts and stops, and where it stops at the end here in the last dwell period. This is another 12-inch long diagram, and it's 1.5 inches in height, as opposed to 2 inches from assignment number 9. This is divided up into 10 equal increments this way, and 10 equal increments this way. I took out a lot of the construction lines in here just to kind of clear it up and clean it up a little bit. This has 6 increments this way, but it has 10 increments this way, 10 degree, or not 10 degree, but 10 increments of angle in here, because it makes the profile turn out to be a little more accurate than just 6 and 6. This is harmonic motion that you've used in assignment number 9, and this is modified uniform motion. There's a little radius right here at the top and a little radius down here at the bottom, so that it doesn't jerkily start and jerkily stop at the end, at the start of the drop and the end of the drop. It transitions into it a little bit. This is a 0.75 radius up here. How did I get that? Well, it's 1.5 inches in total height, and if you come down to the halfway point, that's 0.75. That would be the center line of an arc that would be drawn in here. It would be easiest if you used that center point and drew a 1.5 diameter circle here and a 1.5 diameter circle here, using line command and the tangency option. Make the line tangent to the edge of the circle up here and down here, and then trim it out. That's the best way to get that line in there. You didn't really need to know that, but I'm telling you anyway. Extra bonus material. All right. Okay. Same kind of thing. 0.13 line weight on your construction lines here for the grid, and 0.53 line weight for the actual profile line. Actually, you're not having to worry about that. I already did that for you. Come to think of it, as you insert it. Never mind. All right. How are you going to start? Well, what you can do is go ahead. I'm going to put layer 0 on here. You can do the insert command. You can go out here and browse and get it off the M drive, CAD folder, 255 kinematic folder, AutoCAD drawings, and CAD 255 assignment 10 drawing. Open that up and insert it and plop it into the drawing. I put a label on it just so you know that you got the right one. This should not go into the drawing. To get rid of this, you're going to need to explode the block because it's been inserted. So X enter is explode. And then you can get rid of this text down here, and that'll be your starting point for your drawing. Okay, that's pretty simple. Questions? Everything's clear as mud. All right. And that's over here. And then the actual drawing itself, you will create a side view, which once you get your profile put together, you're going to project over into the right side view. So here's your parameters. Holes, this is the hole for the shaft. Holes can be dimensioned in the view that shows it as a circle. That's your 1-inch diameter there. Don't forget your hidden lines for it. The keyway is shown here. Happens to be labeled as a 1/8 by 1/4 keyway, but you can go back and check to make sure that's correct. And then the hub diameter. The hub is actually a cylinder shape. It would be inappropriate to, and against ANSI standards, to dimension the diameter of the hub out here in this view. It should be dimensioned in the view that shows it as a cylinder shape. So you're going to show that, and since it's lines, you're going to have to include the diameter symbol in here, %C, to get the diameter symbol. Then the instructions were that the plate cam thickness was 1/2 inch. The hub length was 1.5 inches. It didn't say anything about where the position of that was going to be. I arbitrarily said it was going to be centered on the thickness of the hub. You have 1/2 inch here, 1/2 inch for the thickness of the plate, and the other 1/2 inch totals up to your 1.5 inches. Dimension, not a third dimension over here. That will be superfluous and unnecessary. We don't put them all the way across. And center line and hidden lines. All right, how do we go about creating this profile here? Well, you can start by creating the circle for the shaft, and that's going to become your center point. So it's going to be a little eccentric off of the center of where the shaft is located. And then here's the hub diameter. And then here's the prime circle right here. I've shown it in red on the drawing. That's the 3-inch diameter circle here. The prime circle, and let me zoom in just a little bit because I got a lot of stuff going on here. Prime circle diameter, which is centered off of the shaft, the center of the shaft, is where the bottom part of the cam follower would start at. So this is the cam is at rest, and the cam follower is at its starting position, that base point on the cam displacement diagram. Now, the center of the cam follower itself. So if this is a 1/2 inch diameter cam circle, or cam follower circle, then the location of the center of it would be here at this point. To create these offsets, we're going to go back and equate that to the cam displacement diagram itself. It would be best if you created a circle, and I've made it orange here, which would coincide with the center of the cam follower diagram. So this circle is 1/4 inch offset from the prime circle itself. Is everybody with me on that? Okay. And that's at the 0 point. And then I'm going to have equal increments of angle in here. And then I'm going to have offsets, which are going to create where the cam follower would be when the cam actually rotates. So this is going to be here. The cam would rotate and make this rise and fall. But in the drawing itself, the cam profile stays stationary, and we move our cam follower diagram around. Then we come back and make a spline line and use the tangent option and get it to be as close as we can to tangent to that bottom edge of the cam follower diameter. All right. So let's continue on here. All right. Go back to our diagram. We have 180 degrees of rise, and we're going to have 10 increments of that 180 degrees. So if I take 180 divided by 18, I get, or excuse me, 180 divided by 10 gives me 18 degree increments. So every time I hit this, that's an 18 degree increment. 18, 18, 18. And to be able to figure out what the length of this is, remember in assignment number 9, we took 12 and divided it by 360 degrees to get how much linear it went around per degree. And 12 divided by 360 is 0.0333333, and on out. So I can take 180 multiplied by 0.03333 and get the length that this is going to be on my cam displacement diagram. Although it's already been drawn for you, so you can verify that. And that's how that gets developed, which is why I had you do assignment number 9. All right. Once I have my profile established, then this is 0, which equates to that start position, and then I come over the first 18 degree increment. There is a vertical rise from the baseline of my diagram to the first intersection point of my spline. The length of that offset is 0.0381, which I've written over here. That's how much that cam follower is going to move when the cam rotates 18 degrees as it starts out. That's my displacement. All right, everybody got that in your head? All right, so if I come back to my diagram, here's my first circle that is offset 0.25 inches from the prime circle to get the difference between where the bottom of the cam follower is and the center point of that. Because I could move this over and kind of measure off of the prime circle and the bottom edge of the cam follower, but it's a little easier to actually use the center point of it and create my diagram. All right. So notice that this circle is right here, and I've kind of indicated, so here's my first 18-degree increment, which is this center line right here that's going through. And if I offset from this circle that indicates where the center of the cam follower starts at, and this should be then my 0.0381 offset vertical distance. It equates to this first segment on my diagram. So if I actually did an offset, command, put in 0.0381, offset the center line out, it coincides exactly with this other one. I probably should have made it a solid line here, so you can't even really see it. So maybe it would be better if I actually did red here. Put a line in from this point to this point and measured it, and there's my 0.0381 offset in my first 18-degree increment. Okay. Let's take a look at the next two. All right, the next increment over, it's going to be 36 degrees, but it's another 18-degree increment. That distance offset is 0.1462, 0.1462. I go back and I measure, or actually put a line in here, from the center location of the cam follower to that point right there, and measure it, I get 0.1462. So once I have those offsets, I can take this circle and copy it, center line, or center of the circle to center of the circle to center of the circle, and then I'll do one more out here. Actually, I think I have that line in the wrong spot. I need to stick it there. Let me move that for a second.
And we do that for every purple circle?
Yes.
You've only done 3 of them here on the
I'm
example?
going to do 3 of them to show you that process.
Okay.
Make sure I got that in the right spot, maybe. So then the third one is 0.3051. 0.3051. I'm doing these offset. All these offsets are going from my initial center circle that shows the center of the cam follower when it's at the 0 position. Okay, I'm not offsetting from the one that I just offset and offsetting out from that. I'm always going back to the base point. Now let's see if I got my line in the right place here. So if I draw another line, here to here, 0.3051. I just continue that on around. Alright. Also, to help with your drawing, if you, now I made this center line extended out to do some dimensioning, but if you did a center line from the center of your shaft out to about here as a line element, then did an array command and arrayed it 180 degrees and put 11 items in there to get 10 of these. So make sure you've got 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to the 180 degrees. So each of these are 18 degree angles in here. And I'm just progressing out. I get down to 180 degrees, and then whatever that length is, well, it happens to be 1.5 because I'm now at the top of my rise. Then this is going to be 1.5 out to here as well because I have a dwell period. Then I'm going to go back to the other side of the diagram and work my way down. So I would measure or draw a line or something from here to this intersection point. That happens to be 1.3972, and these are 12 degree increments because my drop is in 120 degrees. I'm dividing it up into 10 equal increments to kind of keep my accuracy going here. And if I were measuring from here to the center of where this arc is, that's my 1.3972 inches. I just kind of work my way back. I get to this point and it stays where it is and dwells. Then I come back in here and I create my spline. Just like you did in assignment number 9, I'm going to go from here down to 180 and stop it, and then this is going to be an arc off of that center line, and then another spline around up into here, and then another arc to incorporate that last dwell. How I check these is I have a little cardboard cutout of the right size and shape, and when I get your drawing, this is going to be a plotted out drawing on C size. I get your drawing, I basically stick my little full-size cardboard disc over the top of yours, and if they match up, I'm satisfied. If they don't, I get my red pen out and I make a little, show you where, oh, whoops, I do that wrong, right. Okay, there's a trick to dimensioning this 180 degrees. And the trick is the fact that that should be one line segment to the center line, and this should be a second line segment, not a continuous line from the top down to the bottom. So if I want to do an angular dimension in here, I'll want to put my dimension line on. If I do an angular dimension and pick this line and this line, oh, I must have moved that yesterday. Let's see. It shouldn't. Oh, I didn't move it back. Let's see if I can move it back. That's minus 0.25. I think that's what I did yesterday. So if I do angular, and it's perfectly horizontal or perfectly vertical, AutoCAD goes, I can't dimension that angularly because the lines are parallel. What I suggest is that you take this line and rotate it about 1/4 degree. And then have whole numbers in your dimensioning style for your angular dimensions. Don't have decimal places in it. Then when you put the angular dimension in, oops, I gotta rotate it back. Then I can put an angular dimension in. We trick AutoCAD a little bit and say that, so that's why I had to extend my lines out a little bit to get my dimensioning in here. Something like that. And then when I do another angular dimension between this line and this line, at only 1/4 degree, and you have whole numbers in here in your angular dimensioning style, then it'll show up as 30. And that is such an insignificant amount nobody will ever see that it's not vertical in the drawing. If you're a real stickler for accuracy, you can actually then put the dimensions on and rotate this back the 1/4 of a degree or whatever you did. It doesn't take much, and it would be perfectly correct, but we're not making the cam from this drawing, we're making the cam from the dimensions that are on here. And that will solve the problem of getting the dimensions in. And then you just basically override the text to get the 180 degree rise harmonic motion based on the sample drawing. Any questions? Proper line weights, proper line types, proper text style, proper dimensioning.
Do you want us to keep the offsetted circles in our plot?
You wouldn't have to. It probably would be easier if you didn't.
Uh-huh.
After a while, it gets quite a bit of stuff going on.
Yeah.
For a drawing purpose, it would be better if you could put them on a layer and hide the layer, or you can just delete them after you've done the construction.
Okay.
I'd keep them in there to the last, and then get rid of them.
Okay.
Yeah. And just kind of clean the drawing up a little bit. All right.
Do you want the file?
I don't particularly need the file, but it might help if I have a question about what did you do, and I could open up the electronic file and go in and kind of, if it was a text style kind of a thing, I could go in and go, oh, and I could put that on the drawing. And I did create a drop-off for an electronic file if you wanted to. But I'm looking for the plot to grade and correct. It's a lot easier for me. And that will be it. That's the last assignment. Now, if you get up, there's 8 assignments that have been done throughout this term. That's counting a couple of calculation things and drawings. If you're done with all of them, all 8 of them, and I'm all signed off on them, you don't have to come back. You're all done. So if you get done next week, you can concentrate on something else. You won't have to worry about kinematics. And I won't have to worry about grading projects. And everybody's happy. All right, any other questions? And then if anybody hasn't done a 3D gear print yet, the machines are wide open today, obviously. And that needs to be done.